In this video, we'll change tack for a bit, and we'll talk about one of the mathematical concepts we're going to need going forward. Most of you are taking Calc 1, and by this point, you should have been introduced to the concept of a derivative. Let's use the idea of the derivative to analyze some of our concepts from the beginning of the course. The first topic we started with was kinematics. The most fundamental description of an object is its position. Here we see an accelerating object. It starts at a height of 1.5 meters, and this person throws it upwards at 4 meters per second. It falls under gravity over time. The acceleration is negative 9.81 meters per second squared. We already know how to solve for its displacement over time. We would use one of the toolbox equations. Delta x equals v initial t plus half at squared. Substituting in the values we know, we create the second equation for displacement. Since the object starts at a height of 1.5 meters, we can include that information as well and rewrite the second equation into the third one. The third one is now an equation for absolute position, not just displacement. This equation gives us position as a function of time. If you plug in the time, you get the position of the ball. The fourth equation is a rewrite of the third one, but this has now been written as a quadratic equation. Now, suppose we wanted to know not the position of the ball, but the rate of change of its position over time. Another word for the rate of change of position is velocity. And we can determine the velocity from position through a mathematical technique called differentiation. The technique goes like this. First, the symbol for the derivative of position is dx dt. The d's stand for the rate of change, so this can be read as the rate of change of position divided by the rate of change of time. This is very similar in concept to the slope formula. Now for the calculation. Take the first term in the equation, negative 4.905 t squared. Take the exponent, 2, and multiply it by the coefficient, negative 4.905. Then decrease the exponent by 1. That gives us negative 9.81 t to the first power. We can repeat that for the next term, 4t. Implicitly, that means 4t to the power of 1. Multiply the exponent by the coefficient, that gives us 4, and drop the exponent by 1 to give us 0. That gives us 4t to the 0, or just 4. Finally, the constant term, 1.5. The constant term tells us the original height of the ball, but that's irrelevant to the velocity of the ball. When we're taking the derivative, any constant terms or other pure numbers with no variables attached get ignored. So this is the derivative, the velocity as a function of time, negative 9.81 t plus 4. You could do this process a second time and you could get a rate of change of velocity, that is, the acceleration, negative 9.81. In this course, we're not going to look at very complicated derivatives. Here are the rules for the ones that we will see. They are listed in decreasing order of how frequently we will see them. First, the derivative of a constant is 0. This should make sense. If the position of an object is not changing, that means the rate of change is 0. Second, if you have a coefficient multiplied by a variable, then the derivative is just that coefficient. Next, for every polynomial term, that is a term of the form cx to the power of n, the derivative is cnx to the power of n minus 1, meaning you take the exponent, multiply that by the coefficient, and then drop the exponent by 1. So for instance, the derivative of 3.5x squared is 7x. Next, the derivative of the sine of x is cosine of x. the derivative of cosine of x is negative sine. The derivative of e to the x is itself e to the x. And last, the derivative of the natural logarithm of x is 1 over x. There are 3 more rules that we apply in more complicated cases. If you have multiple terms added, then you take the derivatives term-wise and add them. For instance, if y is equal to 5x cubed plus the sine of x plus ln of x, then the derivative is taken term-wise. 15x squared is the derivative of 5x cubed, the cos of x is the derivative of sine of x, and 1 over x is the derivative of ln of x. Second, if you have any of the above functions multiplied by a constant, then that constant gets multiplied by the derivative. So, the derivative of 3 sine x is 3 cos x. Finally, there's a technique called the chain rule. It says if you have one function inside another, like ln of 2x squared plus 3x, then the overall derivative is the derivative of the inside function times the derivative of the outside function keeping the inside function intact. Here, for instance, the derivative of the inside function, 2x squared plus 3x, is 4x plus 3. We multiply that by the derivative of ln, that is 1 over. So the overall derivative is 4x plus 3 times 1 over 2x squared plus 3x. Consider this situation. If you know that the position of an object is given by this equation, 5x to the fourth plus the sine of x, what is its velocity and what is its acceleration? The velocity is the derivative of the position. That would be 20x cubed plus the cosine of x. The acceleration is the derivative of velocity, or equivalently, the second derivative of position, symbolized as d squared x over dt squared. That would give us 60x squared minus sine of x. There are other calculations that require the opposite operation of a derivative. That's called an antiderivative. In the context of this class, we will use antiderivatives as part of a way of calculating definite integrals. A definite integral requires you to find what function has the given function as its derivative. Once you find that, you need to evaluate the new function at 2 distinct values. For instance, if you know that the velocity of an object is given by this function, v is equal to 6t plus 3, and you want to know its displacement between the time of 5 seconds and 6 seconds, you would calculate it as follows. Velocity is the derivative of displacement, so displacement is the integral of velocity. We would take the integral from 5 seconds to 6 seconds of velocity over time. Since velocity equals 6t plus 3, we substitute that in for v. The dt at the end reminds us which variable we are integrating with respect to, in this case, time. So, what function, when you take its derivative, gives you 6t plus 3? The answer is 3t squared plus 3t. To find the displacement from 5 seconds to 6 seconds, we need to substitute and evaluate those bounds in the antiderivative. First, the upper bound, 3 times 6 squared plus 3 times 6. Then the lower bound, 3 times 5 squared plus 3 times 5. Then take the difference between the two. The upper bound placed in here works out to 126, and the lower bound placed in here works out to 90. So the displacement between 5 seconds and 6 seconds is 36 meters. Another place where integrals play a role is in work. So far, we have defined work as the dot product of force and displacement. But this assumes that the force is constant. If the force changes, then we have to take the integral. First, we need to redefine work. Work is the integral of force over displacement. Now, let's see an example. Supposing you're wearing a jetpack, and the jetpack propels you with a force that decreases over distance. The force is 4x to the power of -3. How much work will you do from a position of 1 meter to the position of 2 meters? Let's set up the integral. The bounds of the integral are 1 and 2. We need to find a function that has 4x to the -3 as its antiderivative. That would be -2x to the -2. We need to evaluate this from 1 to 2. First, the lower bound, -2 times 2 to the -2 power. Then the upper bound, -2 times 1 to the -2 power. The first comes to a value of -0.5, or -1/2, and the second comes to a value of -2. So taking the difference of the two, we get -1/2 minus -2 equals 1.5 joules. The techniques of derivatives and antiderivatives will become important in a couple of videos, particularly when we have to study center of mass.